Welcome to the University of Kentucky's Backyard Streams program. During this webinar, we will learn about low-impact development, which is a stormwater management approach that focuses on stormwater quantity and quality. We will also examine common types of green infrastructure, along with the pros and cons of each one. Unmanaged stormwater negatively impacts streams through changes in the quantity of runoff that reaches streams, as well as the quality of that runoff. Two ways to manage stormwater are through source reduction and green structural best management practices, or BMPs. Source reduction seeks to control the pollutant at its source. Examples of source reduction strategies include using less fertilizer, picking up pet waste, placing trash in the appropriate receptacles, and preventing oil leaks. Green structural BMPs seek to reduce the impacts of stormwater through a structural control, such as rain gardens, permeable pavement, bioswales, stormwater wetlands, and the like. These controls are designed to decrease runoff volume, largely by increasing infiltration and storage in the soil, and by increasing the time it takes for runoff to reach streams by lengthening flow paths and decreasing flow velocities. Low-impact development, or LID, is a stormwater management approach designed to reduce runoff volumes and improve water quality through source reduction as well as green controls. LID is often referred to as green infrastructure, but LID is more than just structures. It also involves planning and management. With LID, the focus shifts from large end-of-pipe or development controls to small lot-level controls. The focus also shifts to controlling runoff from small storms instead of allowing large storms to drive the design. LID also focuses on methods that increase evapotranspiration and infiltration. The reason LID focuses on small storms is that they occur frequently, whereas large storms occur rarely. This graph is a histogram of 30 years of 24-hour storm event data from Lexington, Kentucky. Most storms are small, less than 25 millimeters or 1 inch in depth. LID designs call for designing to capture and infiltrate these smaller storms. Often, a 1-inch rainfall event is used. One key aspect of LID is that it seeks to reduce impervious surfaces. In effect, LID tries to reduce the curve number. To reduce the curve number, LID seeks to reduce the percentage of impervious surfaces in the watershed and/or increase infiltration. One way to do this is by alternating the way roads are laid out. The lollipop and stick configuration, as seen in the top photo, can decrease the amount of impervious surfaces by up to 25% as compared to a grid pattern. However, the trade-off is that less home lots can be built in the same land area. Another way to decrease the amount of impervious surface is to decrease the width of roads and/or use permeable pavement, as seen in the bottom photo. Many older roads allow for the flow of two-way traffic as well as on-street parking. Designing roads without on-street parking is one option, as is installing permeable pavement in areas of low traffic loads and speeds. Rooftops are another large source of impervious area. Building up or vertically rather than out or horizontally is one way to decrease the amount of impervious area in a watershed. Another is to limit the density of development and hence the percentage of impervious area in a watershed. Lastly, changing the design of driveways can reduce impervious surfaces by reducing widths and/or pavement types. In some cases, it may be feasible for homeowners or businesses to share a driveway. To increase infiltration rates, the focus largely shifts to soils. In urban areas, soils are compacted through the construction and development process. Soils are also compacted through human and vehicular traffic. Repeatedly walking along paths in parks and parking in grassy areas are two ways soils are compacted over time. Additionally, topsoils are removed during the development process, leaving behind lower soil horizons that have higher clay contents and hence lower infiltration rates. Practices that target the alleviation of soil compaction, such as tilling or ripping, and encourage the development of macropores, such as through the addition of organic matter and the planting of vegetation, can increase the infiltration rates of soils. Macropores are large soil pores that allow water to easily move through the soil. Hydrologically sensitive areas are largely those responsible for higher infiltration rates, evapotranspiration rates, and/or water storage. Examples include soils such as sands and loams, as well as riparian areas, wooded areas, and wetlands. LID also seeks to disconnect impervious areas, which serve to increase the time of concentration. Time of concentration is defined as the time it would take for a drop of water at the most remote point in a watershed to reach the outlet. Practices that disconnect impervious areas, meaning water produced from one impervious surface does not flow into another impervious surface, decrease the time of concentration. In other words, it takes longer for that water to travel from its source to the watershed outlet. Examples of ways to disconnect impervious areas include sending roof runoff into vegetated areas rather than to driveways, and directing parking lot runoff to infiltration promoting best management practices such as rain gardens and bioswales. Another way to disconnect impervious surfaces is to promote the development of sheet flow rather than concentrated flow. Sheet flow is dispersed over a larger area, meaning the depth is quite small. Because of this characteristic, sheet flow promotes infiltration while also keeping shear stresses low. Encouraging sheet flow over vegetated areas further slows down runoff due to the friction or roughness of the vegetation. Another way to increase the time of concentration is to increase drainage flow paths. Longer flow paths mean runoff has a longer distance to travel. When the distance traveled is lengthened over the same change in elevation, slope is decreased and hence the ability of water to erode is decreased. Also, surface roughness is increased by incorporating thick vegetation, thus slowing the water and providing it with more opportunities to infiltrate. Maximizing sheet flow will increase opportunities for infiltration. Vegetated swells like the one seen in this photo are a good technique for slowing and spreading runoff. A common question is, which type of green infrastructure BMP is best? No one type fits all locations. While budget is a driver for all projects, other aspects must be considered when selecting a green infrastructure BMP. Consideration must be given to site constraints related to space, soils, slopes, distance to the water table, proximity to building foundations, distance to bedrock, and maintenance requirements for the BMP. Since LID techniques focus on infiltration, it is important to understand any site conditions that limit infiltration. For example, soils with high clay contents have low infiltration rates, while soils with high sand contents have high infiltration rates. If soils are clayey, they will require the addition of amendments to alter their physical properties to promote infiltration. Green infrastructure effectiveness is also tied to slope. Spreading water over a larger area increases the volume of water that it can infiltrate. Flatter slopes allow the development of larger BMPs such as stormwater wetlands. For BMPs that help filter pollutants, such as riparian buffers, steeper slopes require a wider riparian buffer than flatter ones. Steeper slopes create faster flows. Distance to the water table is also a concern. If the water table is close to the surface, then the ability of the LID to infiltrate water will be limited. The same is true for bedrock. When infiltrating water hits a barrier it cannot easily move past, water will begin to back up. The rate at which water can infiltrate will decrease drastically. To prevent potential damage to buildings, strive to maintain a minimum distance between the LID and building foundations. Since some green infrastructure BMPs promote infiltration, it is important not to infiltrate stormwater into the building's foundation, as doing so could weaken it. Take the time to fully understand the amount of maintenance required for the BMP. It is important to budget for this maintenance, as failing to do so can result in reduced performance or even failure. Keep in mind that some BMPs will require maintenance multiple times per year. The level of maintenance may taper down as the BMP matures, as with the riparian buffer, but it may not, as with permeable pavement. Also keep in mind the visibility of the BMP. BMPs that are more visible to the public will require a higher level of maintenance to meet public expectations regarding aesthetics. Because no one green infrastructure BMP will work for all sites, it is important to consider a variety of options. Commonly implemented green infrastructure BMPs include rain gardens or bioretention, bioswales, riparian buffers, rainwater harvesting systems, green roofs, and permeable pavement. Rain gardens or bioretention systems are shallow depressional areas that use a conditioned planting bed to filter and infiltrate stormwater. A conditioned planting bed is one in which the soils are amended to increase infiltration rates and to support plant life. Some amendments are also designed to provide enhanced pollutant removal. The difference between rain gardens and bioretention lies with the underdrain. An underdrain is a system that directs parts or all of stormwater that infiltrates through the soil media to the storm sewer system. Rain gardens do not use an underdrain system, while bioretention does. Rain gardens are often planted with flowers and grasses, though trees and shrubs can be used as well. Vegetation selected for use in a rain garden must be able to withstand both wet conditions, as when stormwater ponds, as well as dry conditions that occur between rain events. In addition to infiltrating and treating stormwater, rain gardens are aesthetically pleasing and can serve as good pollinator habitats, and are popular green infrastructure BMPs with homeowners and businesses. Bioswales or vegetated swales are a combination of an elongated rain garden and a very wide vegetated channel. Bioswales are designed as surface conveyance systems for stormwater. However, they are designed to spread out the flow to promote infiltration. These BMPs have an amended bed, much like a rain garden. Vegetation is selected to handle wet and dry conditions and to have the ability to withstand periods of concentrated flows. Riparian buffers are another popular urban BMP. The vegetation in riparian buffers offers a number of ecosystem benefits depending on the size of the buffer, land slopes, and vegetation type, among other things. Riparian buffers, particularly the grass component, can trap and filter sediments. This function is important not just from a sediment perspective, but also because a number of pollutants are sediment bound, meaning they are also transported with the sediment. By filtering sediment, you can also filter other pollutants. The vegetation in riparian buffers also helps build and maintain stream banks. Vegetation with deep, thick roots helps to hold the stream bank soils in place. Riparian vegetation also works to reduce and dissipate energy, not just along the stream banks, but also along the floodplains when the water exits the banks. Vegetation increases roughness, which slows flow. Riparian buffers store water through features such as vernal ponds and wetlands, and help recharge aquifers. While vegetation helps transpire water, its roots also help loosen the soil, thereby allowing water to infiltrate more easily. Lastly, riparian buffers provide habitat to many creatures such as frogs, salamanders, birds, and mammals. Buffers provide shelter and food. Rain barrels and cisterns are often used by homeowners and some commercial establishments to harvest rainwater for uses such as irrigation, flushing toilets, or washing vehicles. The photo on the right shows a 55-gallon drum which has been converted into a rain barrel, while the photo on the left shows an above-ground cistern used in agricultural operations. To increase the volume of stormwater stored, rain barrels and cisterns can be connected in series. Green roofs, also called landscape roofs and rooftop gardens, consist of an engineered soil media and plants. Green roofs can be relatively simple in design, consisting largely of hardy ground cover plants, or can be complex with a park-like setting. Rainwater falls on the green roof and undergoes evapotranspiration. Rainwater is also stored in engineered soil media. Excess rainwater is directed to the storm sewer system. Permeable pavement is largely an infiltration BMP, though the design does account for some storage. This BMP allows stormwater to percolate through the pavement and infiltrate into the underlying soils. Permeable pavement looks similar to standard asphalt or concrete, except void spaces are created by emitting fine materials. Numerous types of permeable pavement are available, such as permeable concrete, porous asphalt, and concrete grid pavers. Each urban BMP offers different benefits with regards to stormwater management from a water quality and water quantities perspective. Bioretention or rain gardens, for example, are considered highly effective at infiltrating stormwater, while rain barrels and cisterns do not infiltrate stormwater. When selecting urban BMPs, it is important to evaluate their effectiveness in terms of stormwater quantity and quality and in light of the project goals. Thank you for completing this webinar on low-impact development. To learn more about LID and green infrastructure BMPs, check out the publications and additional information sections. For additional information on backyard streams, visit www.uky.edu/BAE/backyardstreams.